So again, welcome everybody. Today I will talk a little bit about taxonomic name harmonization and give you a little introduction onto what that means and how we can achieve that relatively straightforward. So the idea behind this is, of course, we have a lot of different species on Earth, and these species have been classified, and there were a lot of different classifications from very ancient ones, like the ones that have already been proposed in Greece, or like Haeckel proposed here to see in one of these pictures, or more modern ones that are here. And of course, these classifications, they differ. So at the end, they kind of relate to taxonomies, so to ways to sort and order different species that exist on Earth. And the problem that we can come to is that when we have different data sets from different people that we get, these people have used different taxonomies, so different ways of classifying the same species. So in this data set 1 and data set 2, for example, you see we got data with different species, species 1 to 5 in the first data set, and species 1 to 6, 7, 1 and 2, and 6, 7, 8 and 9 in the second data set. And we see, okay, the first two names are the same in both data sets, but species 3, 4, and 5 is unique to dataset 1, and 6, 7, 8, and 9 are unique to dataset 2. And the question is, are these really different species, or are they only names of the same species? And to sort this out, we use taxonomic reference databases. So these reference databases are basically tables that store the names that have been used for different species. And they not only store the names, but they also tell you name A is a synonym of name B. And using these taxonomic reference databases, in this example, for example, we can see that actually our input would be here on the left side is species 1, 2, 3, 4, and 5. And our taxonomic reference database tells us the names of species 1 and species 2 are correct, but 3, 4, and 5 should actually be 2, 4, and 5. So 4 and 5 are also okay, but the name of species 3 is actually a synonym of another name, the one of species 2. And on the other hand, we see we have our other data set, and there we have species 1, 2, 6, 7, 8, and 9. And here our reference database tells us, yes, 1 and 2 are the correct names to use for these species actually, while the name number 6 should actually be name number 4, and name number 7 should be name number 4 also. And so when we now relate, and name number 8 should be name number 1, and now when we relate these two data sets, we can actually sort out which names belong actually to which actual species. And so we can then combine our data in a meaningful way. So that's the idea behind the taxonomic reference databases, that we de-synonymize the different names. There's a lot of tools in R that you can use. This is a snapshot from publication that actually looked up all the different databases and all the different R packages that are available to de-synonymize names. And you can see it's a complete mess. I mean, you would not know where to start, where to end. It is just a lot. But fortunately, yeah, we don't have to ask all these questions in most cases. So in the in case you really want to find out for a very specific taxon what you should do, you can have a look at this publication there that Matthias Grenier has provided. And you can also read a bit on the background of name harmonization in these recommended reads. But there is fortunately the one tool that we can use, and this is one from GBIF, and we will do this in a minute. So the idea will be that we have a name list that we extract from our data sets, and we get different old names. And the first step, what you would usually do with these names is so-called name parsing. That means cleaning these names, basically looking up that there are no confounding characters, no problems in these names that can make it more difficult to match them against the reference database, and then you would get a cleaned named list, and then you would do the actual process of name resolution using a reference database, and you would come up with the resolved names. And the resolved names, as you can see in the second line, they would not always be the same, because, for example, Acroelimus turneri turns out to be a synonym of an accepted name, which is Elimus turneri. And so at the end, these names may be different from the ones we got in the beginning, but they are resolved. And that means that when we use different data sets, we can get the correct names for all of them and match the data that belongs to each species. So the idea that we will do now is that we will open the Jupyter notebooks that you can get from the link that Juliana provided to you. And we will get through them. The first example is the name parsing example. That one we will not do now because we are a bit late in time. You can go through it by yourselves. It's basically, it has a lot of explanations in it, and you can run the code line by line and see what's going to happen. So the name parsing part, so the one where you would take very messy names and clean them using the GBIF name parser, we will not do now, but we will do the second example, which is the name resolution example, where we use the GBIF API to clean some names that we got provided that have a lot of issues with them. And I show you a bit of the problems that can arise and how we can solve them. And we will also do the third part, which is the name resolution for the actual data set in our course. But this one is fortunately quite clean, and it will be relatively easy to do. And what we will do in the course is now, I told you that there are a lot of different reference databases, and we will use the one from GBIF. The advantage of the GBIF reference database is that, first of all, it's very comprehensive. So it includes animals, fungi, and plants. And it is also relatively up to date. So the people are working all the time on refining this taxonomy based on new taxonomic information. And it is also very fast. So the API is doing fuzzy matching for you. And it is also providing a service that is relatively good to use so that you can easily work through a lot of names in a relatively short amount of time. And this is something that we will see now. So with this, I would end this presentation and open the first new Jupyter notebook, which is the name resolution one. What you should have opened now is basically this here. Maybe you don't have the logos here. So the idea in this script is to show you how you can actually de-synonymize the names that you get from your collaborators in different taxonomic data sets. So what you need is, as is written here already, you need the sample names list that is provided, that was provided also on Zenodo. You need the functioning R environment that you will all have, and the data table and RGBIF packages installed. So we can just slowly start because, I mean, the Jupyter books, they are made in a way that you can actually run and do the code more or less by yourself. So I would just start to explain what we are doing step by step. And the ones that still have to install the packages, they can just then run all the cells that we have already passed afterwards, and then they will be on the same place where we are. So the idea in the first part of the script is, of course, that we get our data set and we get our packages loaded. So I do that here in the first cell. We have the data table package, which is basically used to handle the data sets, and the RGBIF package, which will allow us to easily access the GBIF API. So what you will have to adapt is the working directory. So you will have to put it to where you store your data on your machine, or where it's stored in the Jupyter Hub folder. And then you can read in the plants data set. And this data set here, before we have a look at it, there is a little problem that can arise if you get data from a lot of different people, especially all over the world. that the encoding of your data may be different. So there's different ways of to encode different character sets, and we have to check that the encoding is correctly displayed and that we also can use it in a way that we can actually work with the data. So first of all, what I do here is to check what kind of encoding is put for our R here in the moment. So the console, my R console runs with a Germany UTF-8 encoding. So Germany just means that date and time is displayed in a way that it is usually displayed in Germany. And UTF-8 is the important part of it. That actually means that all the characters from the UTF-8 scale are actually displayed. So you can try that for yourselves by running this code cell. And if it does not show UTF-8, then you should change it to it. So for example, here in this line, I show with the sysset local command, you can actually put it to Germany UTF-8, but you can also change the local to whatever other UTF-8 flavor, so to France or whatever you would use. It's just important that it is UTF-8. Then, when we know that our console actually works with all the different characters that can appear, we can actually check whether our name data set is working with, has the correct character encoding. And what we can see here, when we run valid UTF-8, which is a function to check whether the data set is correctly encoded, we see that there are some that are not correctly encoded, 73, and most of them are correctly encoded. So we have also here a second part, which is the plant's name parsed, where I have already corrected the encoding. So when we find names that are not correctly encoded, like the ones where it says false, when we run the valid UTF-8 column, we can change the encoding to a correct one. And for example, what we very often find is when people work with old Windows machines, that their encoding is still what Windows was using until Windows 10. So a very specific encoding that is only used on Windows machines that will lead to unreadable characters when we import them in your Windows versions or also Mac or Linux distributions. And the good thing is that there is an easy function to solve this problem if the encoding is wrong. So when we find things that are not correctly encoded, we can use the iconf function from R that actually is able to reconvert data that comes in Windows encoding, a specific Windows encoding, to UTF-8. And we can run this code, and then we get our problem solved. So what we can here do, for example, we can check once which of the data is wrongly encoded. Just to get an impression. And we see when we run that we get a lot of weird characters here. And these are the ones that are Windows specific and that are not in UTF-8, which is used by Mac or which is used by Linux or also the newer Windows versions. And if we run this function here, we will get rid of all these characters that we can just see here. But as I said, in the data set that we have loaded here, the one, then it is already the plant names parsed text, it is already cleaned. So to run actually the GBIF backbone is relatively easy. There is a function that is called name backbone checklist, and you just give this function the names from the plants or from whatever animals that you have. And it is about 5,000 names that we give here to this function, and 5,000 names will take about 30 seconds. So it's relatively convenient to do it. If you have larger data sets, of course, you will take more time to run this. And you see it's working for a time. Yeah, but it should in general not take much more than half a minute to run this function. And we can have a look at the structure of what we get back. So what we actually sent to GBIF was just the name, the single names, and we get a complete classification back. So what we get is a value for the confidence this GBIF has in the classification that it did. It tells us whether actually things were matched. It tells us whether the names that we found are synonyms or if they are already the correct names of the species that we wanted. It gives us the usage key, so a key to actually always reference these names, the scientific name, canonical name, and other data that is related to the phylogeny of the species that we were looking at. And there is one column that is especially, let's say, important in this case, is the column kingdom. And we know we have provided plant names. So one good check would, of course, be to check whether we also only got plants. And what we can see here, if we run it, that we got mostly plant names, but we also got some fungi. And we got also some names, that one name that was classified as an animal. This can, of course, happen because, first of all, there's a very low percentage of scientific names that can be animals or plants. And there is, of course, also the possibility that our data set is just not clean enough and there are some real data that we would not expect in there. We can have a look at the names that are not plants, and we see, okay, we get here a lot of names that are classified as fungi. And I can tell you from where this data comes from, which is an old distribution of TRY data, that in TRY there are actually also lichen species with traits there. And these here are real lichens. We can see from the match type that is exact, which means that the name was found exactly as it is, that the GBIF is quite confident that these are really fungi. We see one that has a fuzzy matching. So here, for example, we see that there was a spelling error in this name, in the epithet, in contra poenda. And we see that GBIF has corrected it to contra ponenda. So we also get spelling errors sorted out. And here, finally, we find our animal, which is Trifora minima. I have looked this up already, and I have found that actually this can be a mollusk, but it can also be an orchid species. So what we can do if we find things that we would not expect is that we can tell GBIF, well, we think that these are actually really all plants. So we can give it a parameter, kingdom is plante. What that means is that GBIF will first try to still fit the name, but when it is in doubt, because there is a name that can be an animal or a plant or a fungi, then it will select the one that matches better to kingdom is plants. So we can try to do that when it is not in doubt, because there is only a fungi name, then this will not change the output of the function. But we can run it again, and these are only 40 names, so that goes relatively fast. And we see that there have been no changes to all the fungi, so these are really fungi names. We can do what we want, but Trifora minima has been changed to a plant name. So we see here the author is COGN, and here before the author is Pese, 1871, because in animal names you put the time of the description behind. But we see these are two different species. One is an animal, one is a plant. And actually, if we put kingdom is plants behind, we can make sure that GBIF looks at plants preferably. So if it has the choice, it will always select the plant. So we got that one sorted, which is nice. And what we can do is then input this data so that we get this update that we just have plants and fungi in our data finished. Now we can have a look at the different match types. The match types tell us whether there was an exact match, so when the names were found in the GBIF database exactly as they are spelled. If GBIF had to do some fuzzy matching, so if there were some spelling errors inside, which is very helpful if you get data from different people. And it also gives us higher rank and no match. So exact and fuzzy is normally fine, but we should have a look at the data that comes back with the information that it is higher rank. Higher rank means that GBIF was not able to fit the data in the taxonomic classification that we thought, but in a higher level. For example, here we have the first 15 matches that were only matched as higher rank, and we get species names, but our GBIF just gave us back genus names. So this can sometimes happen because if GBIF is not able to find these species in its backbone, it will tell us, well, I don't have these species, so it will try to just fit the genus name, and this is also okay in some cases because you cannot work with species that actually don't exist. But we see also that we sometimes may get some problems with that. For example, Calluna vulgaris here, I would think that one was matched correctly as a species, but here Campylospermum, we see it is only matched as a phylum, as Tracheophyta. And there we may be able to do something a little bit better. So what we can do now is that for the species, for the names where we got family matches like Avena nervosa or Bohemia spicata, where we would think that it should be possible to match actually just the genus, we can rerun the GBIF API and only provide the genus name. To do that, we just select the data set that is higher rank and where the resulting rank was in the family, order, or phylum part. Like these ones here. And we can just select the genus names and run them again. And what we see here is now, for example, for Avena nervosa, which we before were just classified as being a family name in the family Poaceae, where the name was changed to Poaceae, or for Böhmeria spicata, where the family name was just changed to family Orthicaceae. It has just been changed to the actual genus names. So when we just search for the genus names themselves, our GBIF is actually able to find that these are real genera, and it's not giving the higher rank family for them. So that gave us a bit of a better classification, as if we would just have left the higher rank classification here, where these complete species names were just matched on the family basis and not on the genus basis. So this is something that we can always do. And as we can see, this has already reduced the number of higher rank species a lot, but we can still have a look at the ones that were not matched. So let's see the names that were not matched. So when we have a look at them, we can see what very often occurs is that NA values are given as the species name here. This is of course a problem that is from the data itself, but this can sometimes happen. Or we can also see that there are some special characters here, for example, A with a hyphen, which is very often a bad conversion of a former hybrid sign. And we can try to solve these problems and clean the names a little bit. We would normally do this in the name parsing part, but if we only find that when we do the matching and find the match type is none, we can also do that now. So what we can do here is just remove the NA part from behind the names. So when we look at these names, they were quite a lot. As you can see here, it's about 40 to 50 names that are just genera with NA at the end. And this made that the GBIF name parser could not match them. So we can also have a look at the former hybrid sign that was converted to a hyphen here. That is also a problem for the name parser, and we can also remove that one and run these things again. We also get a problem with uppercase names. You can see here that we have a lot of names that are completely uppercase, and this is also a problem for the GBIF name parser. Also this, it will always give you no match. So what we can do with these names is that we can convert them to first letter uppercase and rest lowercase so that we are able to use them. So this is basically done here. These are the old words, and this makes them first letter uppercase, then lowercase. And when we now run this all again, we see that most of the matches that were non-matches have completely disappeared. We have exact matches, fuzzy matches, and higher rank matches now. And if we check the higher rank, we see that there were some names that GBIF could not classify well, like these ones here, that partly may be things that are definitely no scientific names, like grass ecosystem, for example. That is, of course, not a name that you would expect. Or irid, which is just an English name. And there are other ones that have issues in them, but most of them were actually matched. But what we need to take care of, because we informed GBIF before that kingdom is plants, it will always tell us, even if it did not find a match to the name, that because it matched then just the kingdom itself, it will give us always kingdom plants, also when it did not find any real match. And these ones we need to remove again. So what I do here is that actually the ones that got a new scientific name that is plants, the match type was changed to none, and the scientific name to NA. So at the end of the name matching process, we get most of the matches matched exactly, some matched as fuzzy matches, some as higher rank, and some were not matched. And the ones that we have actually matched as higher rank matches were mostly genus, phylum, and species. And we can have a look at how many of them were actually already accepted names and how many were synonyms. So we, using the GBIF API, we were able to actually match about a fifth of the species that were synonyms to their correct names. And if we look at the phyla that were in the data sets, we see that there were a lot of some fungi, some bryophytes, some liverworts, and most of them were actually vascular plants. So all but 14 names could at the end be classified. And if we look again at the structure of the results, the link to GBIF that you would keep for later use would always be the usage key or the accepted usage key, depending on whether a species name is accepted or not. So for unmatched names, we will make sure that there is no GBIF key in the data set. So the ones that were unmatched, for every species, we will first take the usage key. For the ones where we have also an accepted usage key, we will take the accepted usage key. And for the ones that were not matched, we will put the GBIF key to 0 in the results, to NA. And this will finally allow us to take the keys away for us. And now we still have to work with the names. So we will take the GBIF keys as a result and also the names of the species. And as there are different ranks that we matched, we have to take care that for varieties and subspecies, when we need to get the name that GBIF actually provides us, we take the name that is here in the canonical name. And later on, we can join all these results to finally put them into our old data set, so that we in the old data set have the old name that was actually provided by the collaborators, a new name that was provided after the name parsing that removed some of the problematic characters. We get the GBIF key for each of the names that we can use to later get any other information like distribution information from GBIF or match it with other data sets, and we get a resolved GBIF name finally for the names for the species that we find here. For example, in this one here, Abarema curvicarpa, we see that there's actually another name because this is a synonym of this one. For others, it will just be the same name because they were actually matched. For infraspecies names, they have to be corrected a little bit. But at the end, the data set like this allows us to work with these names and continue with the GBIF keys and the GBIF names. So I'm sorry if this was a bit fast. We will now just go to your actual data set. This one is much smaller and also does not come with all of these problems that we get here in this part of the lesson. So I can just open the other notebook that has just our data that we got. So we got the data sets TRY reduced CSV and GBIF1 CSV. And we can read them in again, do the name harmonization with both data sets. I mean, both data sets are quite large. But if you look at the number of unique names that are actually in both data sets, they are relatively small. So if we run this, we can see that in the first data set, which is the one that is the TRY data set, we just got 41 different names. And in the other one, which is the GBIF data set, we get a bit of a mixture. We get about 3 names that are forms, so that are infraspecies names, 4 names that are genus names, 48 names that are species names, 12 that are subspecies, and 5 that are variety names. And of course, running this through our GBIF was quite fast because it is also a quite clean data set. We will not get a lot of problems with that one. But now we need to match both of these data sets. And to do that, we can use again the usage key or the accepted usage key as we did before. As we know that the TRY data set has only species names, while the GBIF data set has lower taxonomic ranks like infraspecies and higher ones as well. And we want to work with the species level for our data that we have here, we can use the species key in GBIF. So the species key always provides us with the actual key of particular species. Even if we matched an infraspecies, we can still get the species key for that one. And if you see from the TRY and the GBIF data sets which keys match, we see that it's quite a lot. But we can, of course, also check if there are names that are only in the TRY dataset or only in the GBIF dataset. And if we check for these ones, we can see that there are 2 names in the TRY dataset, Pinus radiata and Quercus macrantera, that we don't find in the GBIF dataset, and there are a couple of names, Pinus, Quercus rosacea, and a couple of others that are in the GBIF dataset that are not in the TRY dataset. And of course, we could say we throw them away, but sometimes it is worth having a look because sometimes we can have the problem that the same name can actually have different authors, but these are only spelling errors. So sometimes different authors have actually described different species and given them the same names, but sometimes, as we can see here, we have Quercus macrantera in the GBIF dataset, and the author is Fish and May, and we have Quercus macrantera also in the TRY dataset, and the author is Fish and May ex Hohenstein. So here, these author names are quite similar, and what we can see here is that just one name was put into the GBIF backbone several times with slightly different author spellings, but these are actually the same species. And what we would have to do here, we could match them by just their canonical name, which is basically the name without the authors, because Quercus macrantera and Quercus macrantera is occurring in both data sets. So this is what I write here. There are some, but we can see that Quercus macrantera appears in both data sets, just with different authors. And we can check if this is the case for others too. So what I do here is that I actually look up if the species that are not matched in the respective other data set do occur as just the names in the other data set. So we can see in the first case of the TRY data set, we had two names, Pinus radiata and Quercus macrantera. And the second one was actually found in the data set. And in the second case, we can see we have about 10 species, and we see that none of them is found except the third last and the last. So Cetrus atlantica and Quercus macrantera are also found in the data set. So Quercus macrantera we see is also here in TRY. Why Cetrus atlantica? This is a bit surprising, but it can of course be that we have just another match in both data sets of this Cetrus atlantica that we do not actually that has other authors. But as it is in both data sets, it was not shown in the difference between the two. So we can check this out here. And we see that there is actually another Cetrus atlantica in both data sets. So in the TRY data set, we have Cetrus atlantica with this author here. And we have it also in the GBIF data set, but in the GBIF data set, we have additionally Cetrus atlantica with this author, which is very likely the same species, just the author names are written in a different format. So these two, we should also harmonize them. And these two, the Quercus macrantera in both data sets, we should also harmonize them. And the easiest way of harmonizing them is just taking the species keys of one of the species and replacing them by the one of the other species. So let's have a look at the names that could not be matched in the different data sets. So Pinus radiata from TRY has no equivalent in the GBIF data set. And from the GBIF data set, we have several genus names like Pinus, Quercus, Fagus, and Larix that we do not find at all in the TRY data set. And we have also some hybrids that we don't find at all. So these ones and one species. So these ones we will definitely get rid of. But we, for the other ones that we found before, Cetrus and Quercus macrantera, we will keep them, and we will just take the canonical names without the authors to work on with them and use the species keys, but make sure that for the ones that occur several times with the same name but different authors, we just take one species key per name and do discard the other species key that refers to different authors. So what I do here is that in the Quercus macrantera case, for our GBIF, I use the species key from the TRY data set, and in the Cetrus atlantica case of the GBIF data set, I also use the species key from the TRY data set. I do this because I see here the Cetrus atlantica in the TRY data set is the name that occurs in both data sets. So if we take the species key from this here for all Cetrus atlantica occurrences in GBIF, then also this one here will be replaced by the species key of this one. And in Quercus macrantera, we just say that we replace the species keys of the ones in our GBIF, in the GBIF data set with the one in the TRY data set also. So we can do that. And we can remove the species and species keys for the species that we have not matched in either one or the other data set. And now we can put the species and species keys, join them with the original data. And if we now look at the results, we see that here in the TRY data set, we now have the species names as we had them before, and we have also some information about trait values. And we get here the species GBIF name and the species GBIF key. And the same we have for the occurrence data set. We have now the species name from GBIF and also the species key from GBIF. And for the ones that were not matched, we don't have any species and also no species key because we removed them. So what we can now do is that we just remove the rows that have no species GBIF and species key GBIF in both data sets, because these are the rows that have no match in terms of names in the reciprocal data set. And when we remove these rows and look at what this means for the number of data points that we have, we see that in the TRY data set we had 52,000 lines, and we stay with 51,000 lines. So we remove about 600 lines here, which is not too much given the data set has a size of 50,000 rows. And in the GBIF data set, we have 255,800 lines, and after removal of the ones that we don't match in the TRY data set, we still stay with 245,000 lines. So also this is not something we have to worry about. So it's relatively little data that we remove if we take out the rows where we don't have any matching names. So now we should join the tables. So what the idea that we have now is that in the occurrence data set, where we just have X and Y coordinates for species occurrences somewhere in some countries, we want to add columns that actually give us a mean trait value. So for example, mean seed dry mass for all these species, or whatever we have in terms of traits. So we can first have a look at the different traits that are in our data set, and we can see it's quite a lot. It's maybe about 20 traits that we have here in the TRY data set that we can have a look at. And these names are really long. So what I did here is first that I give them a bit shorter names so that it's easier to work with them. I also removed the white spaces and put underscores there, because then it's easier to access the columns in R. So you can do that. Just put a new column that is called new trait name. So when we look at the TRY data set, we see now seed dry mass has now the new trait name seed dry mass with white spaces removed and underscores added, and the other traits have also shorter and more concise names. So what's always a good idea before we now transfer the trait data into the occurrence data set from GBIF is to have a look at the actual traits. So what I do here is to plot the traits per species, and we can have a look on how that looks. So there are some issues in the traits here. And it is always a good idea before we do any calculation of means or whatever to go through these. For example, here we have leaf fresh mass that is likely too high, and to remove these. So after checking these traits, we can see I have listed them here, the problems that I find in this data set. And we can just implement these limits by removing values above a certain threshold and replacing them by NA. So this is what I do here. And the next step would be to calculate trait means per species for all the different traits that we have here. So this takes a little bit of a time, and we can see here now what we have here is now mean values for different traits for the different species. And what we see that there are also some NA values here, and these NA values come because trait data is not available for all of the species. And what we can do is we can visualize this to have a little bit of an idea which trait data we actually have per species. And we can see here that there are some species like Abies koreana that has basically only plant height and seed dry mass as a trait value, and some other species like Fagus sylvatica, Pinus sylvestris, and Quercus robur that have a complete trait data set. So this is something that we should not be afraid of, but we should be aware that not all traits are there in a complete fashion. Let's add the data now to the data set. So now we can actually make use of the species, the names that we have already harmonized between the two data sets. So we know that all names that occur in one data set also occur in the other, and that they are also unique. So we can use the names to actually match the trait names to the data. And what we can see here at the end is that we have still the GBIF occurrence column with the latitude and longitude coordinates, but we also get a lot of columns behind. And these are seed dry mass, SSD, and so on, all the different traits that we have. And what we get here are trait mean values that we calculated from the try data set that we had before. So, of course, for some species, we will have NA values because not all species had data for all the traits, as we can recall in this figure here. But for all the other species, for all the other traits and species, we have the values now in one data set. And what we could do with that is something that you will see in the next lesson. And what is still necessary to do here is just to save this data set, and then it is done. What I did here is just that I used a GZ ending, which is a way to compress the data already so that it doesn't take too much size on the disk. You could easily also just save it as a CSV or a text file, but then the size of the data sets would, of course, be much larger. So with that, we have this new data set, and we can continue to work with that data set in any possible way.